Good morning. Thank you for being here for our presentation this morning. We are the Dustbusters team, and we're excited to introduce our EMC dust mitigation device. Yeah. All right, so starting off with the problem, go ahead and start that. This is some footage from the Apollo 14 landing sequence. You'll see as the lander gets closer to the surface, the visibility is lowered tremendously by dust kicked up from the rocket exhaust. And that is just one of the many issues that we see from lunar dust. And this is what we'll be looking to solve with our dust mitigation device. So the Human Lander Challenge issued this challenge to universities around the nation, managed by the National Institute of Aerospace, and challenged teams of college students to design solutions to this issue with dust, with PSI, or plume surface interaction. And that's the effects of the rocket exhaust on the lunar surface, kicking up the dust, as you just saw in the video. It has some other negative effects that we'll touch on as well. But this challenge was sent out to universities, and that is what we are currently doing. And that's what we've been working on this semester, developing a device that will be used to mitigate PSI, mitigate dust, lunar surface interaction, and that's issued from this challenge. So lunar dust is generally defined as lunar regolith with a diameter of less than 20 microns. That can be positively or negatively charged due to solar winds. And then with that, lunar dust has magnetic properties due to the presence of iron within it. And you see that is proportional to the size of the dust particle and its diameter. And this is thought to have been caused by surface interactions, potentially with meteorite impacts long time ago. And that would generating and colliding and creating this presence of iron on the moon's surface. And that is one of the reasons particles in the lunar soil are particularly magnetic.
So some of the problems that come with the lunar regolith is that it can have very jagged edges, which can cut into and damage materials. Another is that it's been shown that inhaling the lunar dust can have very harmful effects, as well as it can accumulate under the spacecraft and backfill the nozzle of the rocket engine, as well as decrease visibility, as shown in the video. Now, something that is currently being implemented is the EDS, the electrodynamic dust shield, which uses a multi-phase traveling electric field to move charged dust particles. And this is currently used in a lot of smaller scale applications, such as solar panels, optical systems, thermal radiators, flexible films, and spacesuit fabrics.
All right, so in order to get a better understanding of why this is such a big problem, we did a CFD analysis on the actual lander. It's going to be, well, our selected lander, the SpaceX Starship. So they're going to be using the 3 Raptor engines and the 3 Raptor vacuum engines. The properties are shown here on this table for the vacuum engine, because that's the one that's going to be used near the moon. It's this lighter blue one, and then also liquid methane and liquid oxygen fuel, also known as methalox. So this was one of the main results of our CFD analysis. As you can see, the velocity contour. And what we saw from that was a max exit velocity of about 2,616 meters per second. So obviously that's going to lead to a lot of displacement of dust. 2 of the big problems we discovered was going to be the underexpanded plumage flow, which is basically when the exit pressure is larger than ambient pressure, which leads to expansion waves, oblique shocks, and shock cells, which is obviously going to impact the displacement of the dust. And then also plume surface interaction, or PSI, which is when the free jet flow, oblique plate shocks, and wall jet interact at a plate called the triple point, which is going to cause a recirculation of gas above the surface, causing more displacement of particles. So with that in mind, our goal was to redirect this lunar regolith away from the skirt of the HLS containing the engines.
So when first presented with the Human Lander Challenge, our team came up with several initial ideas for possible solutions to mitigate lunar PSI, ranging from using ferromagnetic wiring to generate a magnetic field around the HLS, using a deployable rover that would collect and remove regolith while navigating the lunar surface, or even using a deployable landing pad in order to reduce the effects of rocket exhaust on the lunar surface. However, we ultimately decided on a variation of using wiring to generate a magnetic field based on the electromagnetic properties of lunar regolith, while also wanting a device that was simple yet effective, while not disrupting the aerodynamics of the HLS or requiring separation from it. And here we have a model of our design. And as you can see, it is a copper wire that is tightly wound around a steel housing, which is then bolted to the inside of the HLS. So the basic principle of our idea is based on a solenoid. And what that is a tightly wound copper wire that is coiled around a housing usually made of iron or steel. In this case, we went with steel. And as an electric current is passed through it, it generates a magnetic field around the wiring. And the reason we chose this is because of the fact that, as stated earlier, the most harmful lunar dust particles, those being smaller than 20 microns in diameter, contain iron and will therefore be affected by the subsequent magnetic force. And doing some calculations, which are presented later in this presentation, and assuming that our device is activated at the final stage of descent and that we're landing on the polar region of the moon, we found that we would need to generate at least 8 times the magnetic force of the, we would need to generate a magnetic force that is at least 8 times the strength of the electrostatic force created by the lunar electric field.
Okay, so here you can see a render of the SpaceX HLS landing on the moon. The top thrusters will already be used to help mitigate the dust disturbance, and our device will be along the bottom to help remove what is left from the sensitive areas of the rocket. So for the Artemis 3 mission's landing sequence, the lander will begin its descent from the near rectilinear halo orbit around the moon. And the landing sites are all near the lunar south pole, where visibility is already low due to permanently shadowed regions. So, fun fact, during the Apollo 11's descent, the time between the first visible dust disturbance and landing was 66 seconds. That's a lot of time for, if during low visibility, you could be getting off track. And also for future missions, if you've got infrastructure around the landing site, being sandblasted by dust for 66 seconds, it wouldn't be nice. Okay, so here's a picture of the different potential landing sites for Artemis 3. You can see South Pole here and all of the spotty sunlight due to craters and hills on the surface. So if you land wrong on a slant, especially considering how tall the HLS is, the entire mission could be in jeopardy. So that's why this is so important.
All right, up next, we are going to talk about our power systems analysis. We wanted to determine how much power was necessary to influence the lunar regolith's movement of up to 8 times. To start off, we have a couple of primary assumptions. Our first one was our velocity of our dust, which was in use. We assumed that it would have constant speed and constant direction. That would be going parallel to our HLS. We also assumed constant and uniform material properties throughout our lunar regolith, as well as in our EMC device. We also assumed constant temperature during use. We assumed a temperature of 23 degrees Celsius at launch. This was the average temperature at Cape Canaveral. We also assumed a negative 13 degrees Celsius, which was an average temperature of the lunar South Pole. Next up, I want to walk us through our evaluation of how we came to our power. First off, we created a free pie diagram using a proportionality constant of 8. We wanted to overcome the I'm sorry, is everything okay?
It's okay.
Okay. The electromagnetism of the lunar surface by 8 times using our electromagnet. Our current was then found by setting these two equal and solving for our current using the velocity of our lunar regolith, as well as the material properties. We then were able to find that it would be equivalent to 93.2 amperes approximately. We then moved into our resistance, which we were able to find using the resistivity of copper, as well as the material properties of our wire. This was then found to be 0.115 ohms, which we were then able to solve for our power, which was 998 watts or almost 1 kilowatt. We then ran an analysis if we had a 30-degree difference in temperature. And as we know, when electric coils work at a lower temperature, they become more efficient. We were able to find that our EMC device would be 7% more efficient.
So now that we had known power values for our EMC device, we could combine these with known values from the Apollo 11 timeline and power requirements to determine a load power profile, which is essentially just a timeline of how much power you're using throughout different stages of your landing. So our power profile included descent, resting on the lunar surface, and ascent. So this is a graph of the load power profile. As you can see, the first part of the piecewise is very short. That's our descent. And at the very end, you can see a spike, which is when the EMC device is activated. That's that short 66 seconds that's turned on for. Second part of the piecewise graph is our long resting period on the lunar surface. And then, as you can see, there's another equivalent spike at the beginning of the ascent back into lunar orbit. Here we have a schematic of our dynamic power system. And basically what this is, it just shows how power flows throughout our HLS. So in the center, in this big green box, we have the electrical power subsystem, which is basically the driver for this entire schematic. There are two main methods of power generation with our HLS. Solar panel array housed on the outer surface, and a fuel cell, which uses methalox gas. The fuel cell will direct most of its power to the Raptor vacuum engines in the propulsion system, and the solar panel array will take care of most of the rest of the electronical components. As you can see, there's a controller that will control the amount of electricity given to each subsystem, and each subsystem will return feedback to determine how much power needs to be drawn in the future.
Off of our research, we were able to determine that there would be 4 batteries on board our HLS, which would equate to 122 kilowatts of power. Off of our previous slides, we were able to determine that we would only use 1% of our total power budget, which was on board, which we felt was more than justified as a result of the effects of our EMC device.
So next we ran a material analysis for the enclosure of the EMC device. So here you can see the 3 materials that we compared: 4140 steel, aluminum, and 300 series stainless steel. And then here are some of the properties that we compared for each material. So we ended up choosing 4140 steel for the enclosure for a couple different reasons. Its high strict tensile and yield strength, as well as a decent fracture toughness, combined with its great magnetic shielding and higher thermal tolerance than aluminum, led us to make this choice. It just ended up being the best balance of cost, performance, and availability for the enclosure. So we also ran a material analysis for the wire of the EMC device and found that 4/0 AWG copper wire was the most applicable here. The insulation protects against current jumping as well as any high heat, and the copper was chosen for its low resistivity, which results in a greater current flow and then a stronger magnetic field. To make sure that 4/0 was the best size for the cost and most efficient, we verified through some equations that you can see on the right here. So we also ran a cost estimation for the EMC device as well as how much the added weight would add to the launch cost. So at the top of the table, you can see the cost for the steel enclosure, the wire, the bolts, washer, and the needed battery that we would need, which is really minute compared to the launch cost, which would add about $150,000, bringing the total cost estimation with the added weight to $172,000. So the device itself is relatively cheap.
Great. So then that brings us into the weight consideration. So as previously alluded on the previous slide, weight is something we definitely want to consider and take into account for our system. Various weight saving measures were added. Our initial designs came out to around about triple times the mass. So obviously we had to put some measures to limit that. So some things we included were pockets and slots cut out to decrease the material needed without compromising the strength, and also playing around with different material thicknesses for this steel enclosure. In the end, we got our system weight to be just shy of around 7,500 kilograms. And then so in terms of kind of putting that in context with our available payload, SpaceX has stated that the Starship HLS should have a payload of about 100 metric tons. So with the consideration that this would just be an extra portion added on, this means that our weight added to the system would decrease the effective payload capacity of Starship HLS by about 7.7%. Basically, we felt that 7.7% was an acceptable number, considering that the implementation of this device should have a greater success probability for our landings. And so it's just kind of a trade-off of, you know, being more confident in your landings, and you may be able to carry a little bit less cargo. However, 100 metric tons is a lot. So we felt that it was an acceptable trade-off there. So just going in a little bit more, kind of alluded to before, this is just the weight breakdown here. As you can see, the majority of the weight comes from the enclosure steel, which makes sense. Steel is pretty significantly dense and has a lot of mass. So here it comes out to the most significant 6,000 out of the 7,500 kilograms. Our copper wire, copper is of course also metal, but it is just wire, so comparatively less volume. Our different 720 nuts and bolts. And then we also, in our power budget, we determined that most likely the photovoltaic solar panels would be sufficient for what we did, but we felt that just including a Tesla battery might also give some more redundancy and fail safes. And so kind of it was alluded to in the previous slides, but we just added them there just to have additional power budget that might be able to just be dedicated solely to the system in case, it proves an issue during the landing sequence. So going into kind of more like the mechanical engineering side of the device here, careful consideration was put into the fastening method for what we had. So we iterated on the exact quantity, but we ended up settling on 720 class 12.9 zinc plated socket head cap screws. So the top right there kind of shows what it looks like. The idea is there they would fit into these counterbore holes in the enclosure steel, and then it would be fastened to the inside of the skirt of the Starship HLS system. Then we went through and just used some classic joint equations to figure out the performance of our bolted joints, or our screws, I guess technically. On the right is an example of what happens when we have pre-tension, and we'll have the appropriate clamping force based on torquing the bolts. From there, we isolate out what the slip resistance of our entire system would be based on using 720 volts, typical torque values for volts. And we got to a combined slip resistance of 89.88 meganewtons. From our previous CFD analysis, we figured out what our takeoff thrust would be. And then so just kind of assuming that the takeoff thrust would apply the joints in slip, we get a factor of safety 1.21, which is above 1, which is great, but we also want to consider in the event that the joints do slip, what would be the performance of the fasteners in a bearing type situation as pictured on the left here, where the enclosure is actually on the shank of the fastener. And so we use the von Mises theory of shear failure and determined that our strength and shear was 11,100 megapascals per bolt. And so that gives us a factor of safety 3.44. So that gives us kind of confidence that in the event of slip, the bearing, obviously not ideal, but that the bearing strength of the fasteners should keep the performance intact there. Moving forward into the actual analysis of the structure of the enclosure itself, we determined that the geometry of it was a little too far away from a standard shape to approximate, especially when we had the cutouts. So we decided to go with a finite element analysis method. We created a static structural load case by applying our takeoff thrust as a force, as previously mentioned, and then constraining it on the outer perimeter of the enclosure. And here you can see the results of what we have here. You see we have areas of high stress where the wall of the enclosure kind of meets the flat portion. If we were to iterate on this now, we could add things such as fillets to help decrease the stress concentrations in those areas. But we decided that with a minimum static factor safety 1.74, it's, you know, in terms of aerospace engineering, that's not too atypical. We also chose to analyze the takeoff launch thrust because from our analysis, it was the worst case scenario. That's when we had the greatest loads overcoming Earth's gravity. So we determined that if it could pass the worst case scenario, it should be sufficient for things such as the moon landing, which obviously has less gravity and less thrust needed, especially with the mid-sized body thrusters.
All right, next up, we have our fatigue analysis for our EMC device. So the EMC device actually in the Artemis 3 mission won't experience enough loads or cycles to potentially fail from fatigue, but we want to consider this in case in future iterations, the EMC device was used multiple times, or if it was like transferred from one HLS to another and then used again. So for our fatigue analysis, we wanted to get an estimation for our cyclic stress. We found that by taking the pressure difference as the Starship HLS exits the atmosphere and the stress experienced from that change in pressure. And we found that to be approximately 69.6 megapascals. And as we can see from the fatigue life diagram of 4140 steel, that's not enough to potentially cause the 4140 steel enclosure of the EMC device to fail from fatigue. So if this device were used for multiple missions, fatigue would not be an issue for this device. And lastly, we have a thermal analysis for our EMC device. So there were two sources of heat that we wanted to take in consideration. First, we thought about the initial heating from the utilization of the Raptor engines. So the EMC device is going to be located next to the vacuum Raptor engines, which are only going to be used in space, and all the exhaust from those engines are going to be pointed away from the device. So we decided that the heat from that would be negligible. And the other source of heat that we wanted to consider was the electricity used from operating the electromagnet. And through our calculations, we found that the temperature difference there would only be about 2.5 degrees Celsius. And here's a photo of our ANSYS fluent, thermal analysis of how the heat flux would travel throughout the device. And then this heat would transfer to the spacecraft interior. But since it's only 2.5 degrees Celsius, it's such a small number that it's really not a concern for our design. And we decided that no additional thermal shielding would be needed for its implementation. And here are references, and that concludes our presentation. Are there any questions?
Thank you.
Yes.
This come at Tom. We're waiting for your question.
Yeah, while we're waiting.
If it's a short question.
It's a short question. He says he's typing.
Yes.
It's not a short question.
He's typing them.
Yeah, that's it. Sure, we can wait.
Oh, I do have one short question. Did you guys make that render of the landing? Or is that? where'd you
That
guys
was,
find
that was from, we sourced that.
Hmm.
From YouTube.
Oh, it's from
Good stuff,
video?
yeah.
I didn't even know I didn't know they had renders like that.
It's kind of cool.
Yeah, that's pretty cool. That's good.
Overall great presentation. I mean, the purely in terms of presentation part is so much better.
What is the
Sorry, that's,
We don't know the other group.
We'll take it.
I shouldn't say that. And the logic of the whole thing is so much clearer. Yeah. Okay, first question you did.
Just want to read it out.
Yeah, I'll read it out loud for you.
Yeah.
So he says, I'm really interested in the dynamics of the regolith travel under the influence of the plume and your magnetic field. How much is actually going to get on your vehicle? How much is allowable? And how do you know the magnetic field you're generating is sufficient to do that?
Yeah, I guess probably David and I can jump in for that. With this, like we kind of said, we have to make a lot of assumptions, the specific data on, oh yeah, should go talk here. We have to make a good amount of assumptions. Historically, the kind of CFD analysis for the PSI is pretty complicated. And then so from our experience with, you know, the ANSYS fluent, David here has done a good amount of it, but just kind of it depends so much on the landing site and things like that. There's a lot of variables that it was difficult to fully account for, so we had to make a good amount of assumptions.
Yeah, so what we kind of assumed is that when the exhaust would hit the surface, it would bounce up. The dust
Yeah,
would
I
bounce
think
up at
I think of a slide here at the beginning with
it'd bounce up with roughly the same velocity of the
no,
exhaust.
farther back.
And so we would use the equations for a solenoid.
Back
Sorry, 1 second.
more. It was near the beginning. This one.
Okay, yeah, we would use the equations for a solenoid to calculate how much electricity we would need essentially to generate enough force from the magnetic field to stop that bounce back velocity.
If this were actually be implemented, I would make the assumption that SpaceX probably has some more concrete data from their own analysis team about exactly how much they expected. We already know that they consider it a problem because it's kind of been a known problem since the Apollo missions. But for instance, I kind of mentioned the landing sequence, but they've already have I think it's 24 mid-sized thrusters that turn on during the landing sequence and they turn off the Raptor vacuum engine. So it's definitely something they're already aware of. I would assume that they've done kind of mission or analysis on that. The main way that we approached it was in our math, in our free diagram, we created what's called a proportion, and we called it a proportionality constant. So we know that one thing that we could calculate was all the dust in the, I guess, lunar atmosphere, as they call it, actually kind of floats around there because there's a natural lunar electric field. And then, the lunar dust has an electric charge. And so the way we wanted to try to come up with a number was creating a magnetic force that was K times more than that electrostatic force. We analyzed with different values, I think of 2, 4, and 8.
Yeah.
And eventually we decided picking 8 because we found that our power consumption really was a lot less than we expected from, based on the entire power budget that the SpaceX HLS could produce. So in theory, we could even continue ramping it up more. With our analysis though, the current, kind of based on P equals I squared R, the power it's proportional to the square of the kind of the current, and then the current is proportional to the magnetic field. So there's definitely where's it going to go? Okay, that's finished. Where's it going to go? So it goes in the skirt of the Starship HLS. Oh, the dust. Yeah. So the idea there is kind of oh, that makes sense. Yeah, the diagram. So the idea is it kind of redistributes out. We did consider that it kind of, with the nature of the field, it does come back in on itself. However, we kind of reasoned that the entire exterior of the Starship HLS is made of stainless steel, which is pretty strong material. We figured that would be better redirecting it there. Yeah, exactly. So the idea is the dust would redirect towards the stainless steel. instead of, kind of more sensitive portions of the nozzles of the engine, because if something gets in there, you could potentially, ruin the entire mission. Because, then you don't have a vehicle to go up, whereas if you have kind of exterior damage, it's not as much of a problem, especially since, correct me if I'm wrong, but I think for the Artemis 3 mission, the Starship HLS launches up, docks with the Orion spacecraft, and then gets jettisoned off. So in terms of this specific mission for Artemis 3, we figured that, it's okay if we have some kind of like erosion on the outside. It's much preferable than the more sensitive portions of the Raptor vacuum engines, which would be used going back up into the new rectilinear halo orbit.
Yep.
Do you want me to ask my question?
Okay,
Uh,
that's a new question, sorry.
you said, let's talk about weight.
Hmm.
What was your question? 7 tons is,
Huge.
it is
Very
big.
large.
Most of that does come from the enclosure.
Yeah, the Starship HLS is 9 meters in diameter. So
Yeah. It's a big landing system. I think like that was about how tall that's the Apollo landers would be in comparison to this thing.
mhm. Yeah,
As for ways we could reduce that, there are options, but we don't know a whole lot, honestly, about.
just number 10, they put capacity 8% is acceptable. Okay, I mean, that's understandable. We don't have too much familiarity with, typical mission logistics. I think that's definitely something, if we're to iterate on the design, we'd probably try to figure out ways to decrease it.
Yeah, like
Small enclosure,
we
smaller enclosure.
we see the big factor of make this structural. Okay, so like instead of the enclosure idea, like attach it along the skirt almost directly.
Got it. Okay, I think it's kind of what one of our initial ideas was, right? From our
One reason we also used it was to possibly unattach it. If you want.
Yeah, having this
Kind of touch on that.
having this enclosure does allow us to use this on more than just the one rocket. We can move it to other ones.
Okay, some more structure this way, structure.
Okay.
Yeah, so one of our initial ideas as it was a kind of a crude sketch, but yeah, just kind of directly integrating it into the rocket somehow. I think ultimately desired part of it is, I guess it's also kind of like, it's like we want to design something
Yeah.
a little more than just kind of putting
Part of the
it.
issue is we just don't exactly know what's under the surface. SpaceX doesn't have that.
Yeah, well, but that does make sense. Yeah, we thought that the 7.7% seemed acceptable, but I guess I would probably trust people who actually work with it more on a more daily basis.
Pretty massive.
Yeah.
Is there space actually?
Okay.
Yeah, that's understandable. I think off the top of my head, there's also some materials that are lighter. I think titanium, off the top of my head, is
Even the spinner.
yeah, you can use it a little bit thinner. It's a little weaker, but based on our analysis, we have fudge factors for that, our
Yeah.
static structural and stuff like that. So I think, we can look into different materials there. If it was still titanium, it'd still be pretty significantly, but
Yeah, and incorporating it structurally would probably be the best idea.
what's our requirement?
I believe for aerospace, the
1.5.
general idea is like 1.4,
1.5.
1.4, 1.5, yeah.
You have a question about that?
I'm just waiting for Tom to do this, but.
A new analysis showing what's up, some things like. Yes, so in our just current design, I do not believe we have fillets in the.
We did not.
In the design edge there.
Yeah.
So that's just I kind of alluded to, if it's something that we did want to kind of improve, basically the idea was I kind of all that Yeah. What we're doing is just kind of looking at, but I could probably could adjust the scale of it to reflect more. We did it based on, yeah, I think we did it based on the yield there. Can't quite remember. That was a little while ago, but yeah, still it's
Over designed.
Okay,
okay. I could see that.
Yeah.
Yeah, I think there's
Yeah.
definitely room.
add,
Just like
add fillets, reduce thickness, that sort of thing.
Makes sense.
Same way.
Mhm.
It's a very good point.
Yeah, I think one of our. Yeah, like I said, we put, we've kind of iterated a little bit with it, kind of like things like adding the slots to, kind of cut out that weight. But yeah, I think there's definitely room for improvement and material thicknesses. Originally, I just made some assumptions for like how thick this wall should be, just, how I felt, and then just trying to figure out where we could save a little bit more weight. But yeah, that makes sense. One of our, I guess, like, for instance, we kind of also had to pick just arbitrary coil height as well. So I think we ended up picking 0.4 meters, I believe, is our coil height. So that's that kind of height right there. That's also something that we could play with. Of course, with a solenoid, the more turns you have, the greater the negative strength you have. So if you decrease the coil height, you'll have less turns, but you could.
Yeah, it was 0.4.
0.4, yeah. So that's also an option there. If we want to actually like decrease the height of the structure, decreasing the number of coils, we could then just increase the number of the current going through. But then, like, again, that goes into the powers. So yeah,
The point is there's options.
there's options for here, yeah. But yeah, I think, yeah, I could see that the weight being something that we would want to iterate on further. Understood, yeah. Yeah, hopefully, when we get to work in the, it'll be a good thing to keep in mind once we start.
Final
working.
report.
Yeah.
And also, if we do get jobs in the industry.
Oh, yeah.
Yeah. Oh,
Power profile.
Slide 20.
Thank you for numbering your slides as well.
The crossroad did it. We're not finished.
The power profile.
Yeah, sure.
I also helped on this.
What are we seeing here? What are we seeing here?
This is how much. What's at 60 kilowatts? That little spike is when the device is on.
I think this is for the entire HOS, right?
Yeah.
It's not just for the device.
Yes.
Yeah, this is well, it was based on the Apollo power requirements because we don't know numbers for SpaceX yet. But this can be updated when and if we get those numbers.
But it's for the entire HLS.
Yeah.
Yeah.
Yes.
Yes. Correct.
You need to repeat the question and answer.
Oh, sorry.
Oh, sorry. So your system requires 1 kilowatt for a few seconds just during landing, and then 1 kilowatt for a few seconds right at liftoff. Yes. So our EMC device will only be on for about 66 seconds during each of these sequences.
Maximum.
Yeah,
66.
maximum.
That's very loud.
And yeah, during liftoff, it will be a lot less. It's just because visibility isn't as much of a concern during liftoff. It's just to keep things out of sensitive areas.
There's a weird way to show that most of your graph times you are not operating. Yes, I could see how that's true. It's kind of unclear what power we're referencing. You're right.
Probably need to label the graph.
Yeah. Maybe like start shape HLS fluid. How we can file.
Yeah, I'd go with a nonlinear horizontal scale, stretch out the times you're operating and overlay the mission profile on top of that. This region is launch, this is landing, here's where we're within X meters of the surface, internal device, etc. I
Okay.
think that's good advice.
Yeah, I'm gonna
We'll edit
take a
that
picture
for-
of that. Actually.
This is recorded.
Yeah, these recorded. But the video I will upload. I don't think the video will include lots of chat message. The video. That's why you need to read. Yeah.
Brandon, this is gonna be a you question.
What effect is this magnetic field you're generating going to have on the other systems in the Starship?
Yeah, so that was definitely something that was, I think, one of our earliest things that we considered, right? Because you generating an electromagnetic field, naturally you could interact with the different systems. It's difficult because SpaceX has not released a lot of public information. So they've said kind of generally what the sensors are. They haven't said specifically a lot of what the sensors, where they are. Based on our, we looked at like previous rocket designs, and it seems like the most common place for things like the GNC and all those different kind of sensor systems is above like kind of the engine stack, closer to the top of the rocket. Comparatively, if you kind of look at how much like the actual field being generated by our thing, it's not super extreme in terms of general electromagnetic fields. I guess that's a pretty subjective answer, but I don't remember, but I think our B field was something like 1.1 times 10 to the negative 4 or 5 Henrys. Is that the unit for Teslas? Yeah. We found out was like not too significantly. It's mostly because we have such a large radius. So you remember a solenoid, it's inversely proportional to the radius. So we had to supply a big current, but ultimately the B field's not that strong because we have such a large radius. Part of it is also we designed the enclosure to be steel, and based on our research, since steel is also ferrous as well, it has this thing where it kind of blocks off the field from our electromagnetic field past it, kind of redirects it around. So I guess one potential thing we could do if we are concerned about it is we kind of create like a steel liner around our sensitive portions. So it, in theory, based on our research, it could like redirect and try to prevent it. We didn't think it would be a huge issue considering the distance away from that. Oh, I see. That steel liner. Yeah, that's a good point.
Yeah. I mean, one important thing is that during the time this will be on, is that the bottom thrusters will not also be on. We're using the top thrusters at that point.
Yeah, I mean, ultimately, we considered that we didn't think it would cause a lot of issues, but
Could be wrong.
we could be wrong. We had to make assumptions with the information that we had.
How much of the dust is actually ferrous? Is it fairly homogeneous?
So there's some data about it. From what I could tell, it's a good amount. So it depends on which region of the moon you're talking about. I kind of alluded to, and I think one of the bullet points, the lunar soil is fairly magnetic. Just over time, there's not any weather on the moon, so just over time it's pretty magnetic. The way that we kind of approached it was you have electrically charged, and you also have the magnetic portion. From what we could tell, pretty much all the lunar dust has some charge. And then so deal with electromagnetic, obviously like electromagnetics. the charged particles should also move through the magnetic field. That one's a little harder to know exactly the direction because it also depends on the velocity of the particles that they initially go through before they're redirected. I think I remember researching some articles and it's difficult to say. It's difficult to say exactly. I don't have an exact number. From what I could tell, it's generally charged either positively or negatively based on location and generally magnetic. That's
Which is also why we use 8 times the electromagnetism of the lunar surface.
yeah.
You want to add that.
I think also something to consider is, kind of the plume as well, kind of would hit other dust particles as well, I guess, and then they're not, charged or magnetic and just kind of push it out and around. Yeah, that's kind of some of the assumptions that we were going with.
And like the previous initiatives does have stuff about NASA using the same concept to defend against the dust.
Yeah. EDS.
Yeah,
System.
the EDS. How would you test this? Okay. I don't think it'd be particularly difficult. Lunar simulant is already being created and used at places like NASA, and as long as it also includes like ferrous particles within, then we could turn it on, see how much power is required to overcome specific velocities or stuff like that.
Correct me if I'm wrong, but I think that the NASA DIRT program is like specifically designed to like kind of test out these different methods where where the EDS system comes from. So we could probably work with the NASA DIRT program to see if we could probably get some actual lunar dust and create some experiments with it. Just off the top of my head there.
If I recall, like I can find a lot of that dust out of like Nevada and China. There's like quite a few like deposits that are pretty
similar to
pretty like yeah.
Got it.
In terms of how ferrous content, I'm not sure.
Mhm.
Budget.
Where was the
Mhm. So in the terms of this project, I don't think we were assigned a budget. We just kind of had to just feel what was reasonable. One thing we noticed going through analysis is, like we said, the majority of our cost is a launch cost,
which is weight.
which is the weight. So like you made a good point before. I think decreasing the weight would be probably the primary goal of this design, which would also decrease the majority of the cost.
Yep.
We weren't, I don't think we were assigned a budget in terms of
There's
the,
no requirement, but of course,
Something to
whether you
consider.
like this the better.
yeah, obviously.
Less is more.
Mhm. What's profit, assembly and testing, et cetera, cost. Yeah, so we haven't, I don't think we looked specifically into those further, kind of like, I guess I'll say like installation costs. Obviously, if this were to actually be implemented by SpaceX, then I'm sure there'd also be a lot of design costs and the labor as well. As students, I guess you could say our labor is free there. In terms of
You're paying to do that.
Yeah.
I would say there were, I think it'd be difficult to give, assign a number to all that. It's not something that we considered. I will say in the design process, we did consider installation and assembly where possible. So for instance, we're looking at different fastening methods of our device to the skirt. Ideas such as like welding or things like that. We decided on fasteners just because they're cheap and they're relatively flexible in terms of installation. So kind of the idea we're thinking is you place it in there and you have like teams going in there and you can kind of bolt it in kind of like how you would install like a car, like a tire wheel where you do like crisscross hatching pattern, like a star pattern, as opposed to like trying to weld this 9 meter piece as a structure to it.
I mean, the important thing is it isn't a complex thing you need that requires highly skilled people. Well, it'll require highly skilled people to install, but it's not like something will go horribly wrong instantly when you install it. It's,
That was the goal, at least.
yeah, it's simple, yeah.
You'd be shocked. Well, yeah, that's why I think with design, you always want to, I mean, I've kind of learned you always want to try to make things simple where it can be. And so in our mind, a technician or an installation person should be fairly familiar with, bolts and torquing them down to the correct thing using like a torque wrench versus welding. You'll probably need, some certified welders, some CWIs to check on it. So that was part of the reasoning as well there, why we went with that specific method.
You want to ask some question?
Ask some questions. Could you go to slide 24? Right. Just noted that I can't recall what exactly. Oh, right. So in terms of you mentioned for the steel, the 4140, what is the point of having magnetic shielding? I guess I don't quite understand if you're using a giant magnet. Well, why would you want to shield? I'm coming
yeah.
lane about this stuff. So
Yeah, I guess kind of what we're thinking was, is this kind of just like a general property that we're not using it too much on this specific implementation.
Well, and the shielding from the components at the top, since
So
it's,
is that what we were talking
yeah.
about?
But shielding from the components at the top, so the electromagnetic field doesn't interfere with other sensors.
oh, so this is not completely enclosing the coil.
No,
Okay. And how exactly did you determine the you wanted to reduce on weight, so you decided to introduce these what do you call them, these holes along the side?
The slots.
The slots, yeah. How did you determine that they'd still be structurally sound with those gone?
Essentially, to like be honest, it was a guess. So like the initial, this is kind of a, it's like a rough, I guess I have back on camera. It was a, I don't know if Tom could hear the question. I guess he's basically Harrison's asking,
He's I think he's heard me before.
Okay, probably that makes sense.
I don't know how good this mic is, but yeah.
Got it. Basically this, to go through the design process, we created the thing and it was like 3 times as heavy. So we're like, that's not good. It seemed too much. So then we just kind of figured out like, where could we take the things? I know when I was designing it, like I wanted to have like these 2 rings here to be able to fasten and like, space out the bolts. If you don't have them too close, you could have like bearing and like a whole tear out. So that was like one of the deciding factors, like leaving adequate, at least 2 diameters, whole space in between there. Then we have like the 2 rows. And then so really just kind of like looking at it, the only place that seemed feasible to take, at the time at least, to take out was kind of this flat surface here and the flat surface there. And it's on a circle. So obviously I didn't want to cut away the entire thing because then it would be floating. That doesn't really make a lot of sense. So
FEA said it was fine.
yeah, basically we did this and then went through the FEA and it's like, okay, it says it's fine. So we're like, all right. But like I said, it could be iterated on to further. Yeah.
In terms of saving on weight, I guess like I'm sorry.
Here you go. He says, I'll say on the structural analysis, you showed your fasteners good and bearing. What about the structure those fasteners go through, bearing the holes of your ring and whatever it's attaching to in the vehicle? And what about the loads induced in the vehicle itself?
Yeah, so I believe in our FE analysis, they were modeled with the holes themselves. I know when I've done FE analysis, like for my different like internships that I worked at, just the typical process that I've gone through it is.
Oh, don't say that.
What did I say?
Don't talk about what you did in internships, I'm guessing.
Oh, okay. I mean, it's just kind of the FE procedure, sure. But we typically don't. I guess I haven't.
The FEM at that scale should not have fastener holes in it.
Okay. Yeah, I guess we do have them, not really. This is the way I've done it before, is just typically not putting the fastener pretension load as part of the load cases, just because generally it gives like weird stress concentrations that would be expected, but yeah, we could run again without the holes. I guess I'm not entirely sure.
Yeah,
Do you have like a
we're just
reason,
not sure.
reason for not putting the holes in the FE model? Hmm.
Putting holes in it at that scale.
Yeah, so I mean, that's part of it. So
Very
I
fine
mean,
bench.
it's relatively simple model. I mean, it didn't take that long to run. If it was taking longer to run, I would work on simplifying the model. I just kind of put the general model and I think it meshed in like about a minute or so. So I didn't think that was too bad there, but.
Is this modeled with 2D elements?
Yeah, I want to say that I used 3D tetrahedral elements, but
I think I remember reading that.
I can't 100%. We did this a little while.
There's nothing wrong with saying, I don't know, I'll look back into it.
Yeah.
Just saying.
I mean, I'm not a FE analyst by background or something. I've done for just general things.
You pull up the old report. Sure.
Type structure your model with 2D elements. Okay, yeah, I mean, I guess the more I do it, I would assume I, take the FE class last semester and done a little work with it, it's always stuff to learn. I mean, just the way I figured was they put it up in SolidWorks, FEA, try to run it and it ran. So yeah, but
Good to know.
yeah, definitely something to take into account.
You do elements, you want 3 elements through the thickness, you want usable aspect ratio. That goes at the element count.
Okay. He
I
says,
see.
because you're using 3D elements, you want 3 elements through the thickness and you want reasonable aspect ratios, and that blows up your element count.
That makes sense.
Yeah, I assume if we wanted more sophisticated results, but it would take a very long time.
As a general rule, it ran and I got a result is not a great justification.
Like I said, truthfully,
In the structure part.
okay. I mean, truthfully, I just don't have a ton of experience with it. But
Don't say that in front of buyers either.
well, I'd rather not lie. Yeah,
I don't know is good.
sure.
Okay, thank you, Tom.
Yeah, thank you.
Thank you very much for your suggestion.
Thank you.
Cool.
Take the feedback.
Okay, I've got a few other questions as well. For slide, what's the next slide? Slide 25. So you have those list of functions there. You didn't really go into any detail in terms of what they actually are. Do you mind going over them and their values and such real quick? This is what you have on hand.
Yeah, it's also actually on the power systems analysis. Those were kind of our formulas that we used to derive our general power.
My
Okay.
feeling is that in the presentation
Mhm.
is there's always a goal when you put something on the slides.
Okay, yeah.
If I mean, what conclusion from those equations? Do you want me to calculate something or? Right? If you want to put the equation, you calculate something, put the calculated result there, and what is the conclusion of your calculated results? Simply put the equation without any values, or I don't see the point.
Okay.
Yeah, and I don't see any connection. I did not make that connection between seeing these equations and where you put them on and calculating power system stuff. Like, you want to make sure those are clear.
Makes sense.
Yeah.
Yeah, off the top of my head, I believe that C is that proportionality constant, H is the height of the enclosure there, and or ES is the lunar electric field strength. Mu naught O is the permittivity of free space, and is the number of coil turns. V's expected velocity of the initial velocity of the particles. Rho is the resistivity of copper. L is the length of the wire, and A is the cross-sectional area of the wire. And then this is kind of expanding it. But
Okay.
yeah, no, that makes sense.
And then P is just your I times R then?
Correct. Yeah, I square.
Gotcha. Yeah, when you're going through slides, especially at like the pace at which you need to get through a half hour, it's very hard to tell what your exact goal is, because that just looks like a bunch of gobbledygook from where I'm sitting.
Good question there.
He says, actually, one more, 4 is extremely thick. Would you be better off with thinner wire with more turns and lower current to achieve the same magnetic field?
Actually, when we went through and calculated it, we tested a few different thicknesses, and generally the bigger was better. So we went with 4 because it's the largest that's commercially available.
Yeah, so like part of it, I guess you can kind of see like, we found that it was like proportional to little d squared, and just we looked at, I guess come back up. We looked at kind of like the maximum current that each of the sizes were rated for copper, and we just kind of tested a whole bunch of different different copper sizes or wires of like what I would need to meet the proportionality constant we needed, and generally we just found that, at least from our math, it was saying the bigger wire would have less power requirements. Once again, based on what we found, the power is not too significant of a thing. So if like the thickness of the wire is something that is a problem, there are other choices, but we found this was the bigger wire was the most power efficient. So that's kind of the idea that we went with there.
I was asking a lot of the questions that I was thinking of asking. So I don't remember what else I was thinking.
He says, I'm surprised by that. If I were to look at like an industrial electromagnet or an MRI machine, would I see wires that gauge?
I do not know.
Yeah, I'm not too sure about. That'd be interesting to look into.
So this mission is going to be pretty different because it's going to be going to the lunar South Pole. So the material characteristics are going to be quite a bit different. Do you guys know exactly what the ferrous content of the Southern Pole is compared to the Sea of Tranquility that we were landing in during the Apollo missions?
Is it all negative? If you want to go back to that, I remember doing research on it a while ago.
Go ahead.
Or
Yeah, I think I don't know if this outlines it as well as the research that I did, but there is research on the South Pole, and I can't remember looking at this. I'm almost certain that it's all negatively charged.
And that's just because it is oriented at the South Pole.
Mhm.
Okay.
And where the North Pole would be all positively charged.
So in a way, it might actually be better to land there because we can control it,
Exactly.
potentially control it. Okay.
Yeah.
Okay.
Thanks, we should.
the very beginning.
So since we already have enough technical question, I'm just like talking about the presentation itself. So I feel like the background and introduction part is actually too long because it's like 5 minutes into presentation, I still don't see anything related to design. It's all about background information. So 5 minutes out of 30 minutes is a bit too much.
Yeah.
Right. Because I mean, those kind of background information is same for every group. And when people read the project, they probably already know those background information. The thing that is that you want to spend more time really on your own design. So that part probably is like make it like shorter a little bit. And then I think the initial design, initial ideas. So one thing I want to say that is still like the slides is too busy. On the slides is too much distraction. And also, I mean, for these initial ideas, you can definitely like separate to 3 slides. Because if you put everything on one slide, it's too tiny. And when you talk about like one design, we need to figure out okay, which picture are you talking about? So if you separate to 3 slides, and then you talk different, we can really focus. We know instead of we are spending time to figure out which part you are talking about, right? And also the picture that's too tiny. And one thing I want to say that the page 11, page 40 is actually something I really like. Yeah, so I really want to see something like slides is something that help my presentation. You do not expect the audience to read the information in the slides. So slides like this is like great. And for the power system. So one thing again, in terms of the presentation itself, I was checking the computer because you were staring at the computer. I was thinking like, is there something like on the computer or something? So my feeling is that your presentation is perfect, but hey, we are here. Look at us.
I thought I was speaking with Tom.
Looking at the camera.
The camera shows everything, so
Okay.
don't worry about that.
Okay.
I mean, we are here. Talk to us.
Okay.
Yeah. So that is the part of the presentation part. And page 19. I mean, who is this slide? If you
That was probably me.
why they're like
So much white space.
yeah, make the text larger.
Yeah.
Right. So these are like very simple thing, just pure in terms of presentation itself. I mean, you guys, presentation skill is part of the training in our design class. It's a very important part. So you guys will do a lot of presentation when you go to dentistry or you go to graduate school, you need to go to conference. So these are very simple things to pay attention to. Page 25, I think I already talked about that part.
25.
The one on the equations.
Yeah, I think
that's
that.
about that.
And the order of slides, I think is like, again, I think the logic of your whole presentation is better than the last group, but you can make it better. So again, you have material analysis, and then you have something else, and then you have structure analysis. I want to see that, okay, now this is the project, this is our design, and what's the big picture of design? Different system, different thing we have done, each just a topic, big picture. And for each topic, we have a structure for each topic. Right now, it's more like scattered detailed information. I don't see a big picture. I don't see a structure of each topic. I don't see a structure of the whole project, whole design. So I feel like the order of slides probably can change a little bit because I see some like material selection and then something else and then back to structure analysis. Material selection and structure analysis should be together, right? You have material selection and now we do structure analysis and we see if the structure was fail or not. That's the logic of the structure analysis.
Sometimes helps your presentation to have like a list of what you're going to present on at the very beginning.
Yeah,
So,
it's like at the very beginning you have
the
roadmap.
structure itself.
Yeah.
That helps you build, that also helps you build your own presentation by just looking back at that, making sure everything is within sort of logical order.
Yeah. And can you go to the structure analysis? Yeah, here. No.
Oh, one back.
Yeah. The thing I always say that, the thing I'm really serious, like every time when people say stress equal force over area. When you put tau equal to V over A, is it correct or not? Is it correct or not?
The typical.
Is that calculation correct or not? Tau equal to V over A.
I mean, I thought so, but
Anybody else?
in the sense that it's not. It's the one I know.
When you calculate safety factor or anything, what do you want? That is average shear stress. What is
Okay.
maximum shear stress if it's circular cross section?
Sorry, can you say that again?
So this is calculating for a fastener, right? So it's circular cross section. If it's a circular cross section, what is the maximum shear stress? Because shear stress is not constantly distributed over the circular cross section. You know what I mean?
Yeah, I used the, I think the minor diameter. I use like the minimum area of the bolts, but.
Yeah, I know.
Okay.
V over A is average shear stress.
Okay.
And you know what I mean?
Okay.
It change over the cross section. And when you calculate like, oh, what is maximum stress, what's safety factor, you need to use maximum shear stress. What is maximum shear stress over the cross section?
Okay, well, I thought it was using the minimum area, so you're saying you wouldn't, I guess I'm looking.
So it's sharing this way, right? So yes, I know you're using, of course, using minimum area, and it's started cross section, circular cross section, right?
He says shear stress is 0 at the free surfaces.
Yes,
Okay,
shear stress 0 at the free surface, and also how it change over the cross section for the circular cross section. It's not constant distributed.
okay,
There is a point that is maximum, which is on the neutral surface. What is the maximum on the neutral surface? It's not V of A. V of A is average. You cannot use average stress to calculate safety factor to find out the figure to figure out the maximum stress.
okay.
Yeah, makes sense.
So it's like every time when it's even in my FEA class, it's like whenever I ask about stress, force over area, you really consider like it's correct or not. It's not simply just force over area.
Tom also says, did I hear minor diameter used for the bolt analysis?
Yeah. Well, I used it for the tau. I think I used D, the bolt diameter. But I think for tau, I used just what the minimum area would be, but.
Yeah, so that is the structure analysis and also
We should be sharing through the shank, so yeah, that should be the shank diameter.
Okay.
Good to know.
When you're doing a presentation on a product, and you know, the majority of people here are materials.
Yeah.
You gotta keep that stuff.
you guys.
Yeah, you did.
Page 30. I think one thing here is that we already talking enough about it, but besides just one thing. The thing you mark on the graph is like the 4.7, that is dependent on material, right? What I want to see is a value, what is the maximum stress of the of your structure itself?
Okay.
That is a very important conclusion of your analysis. So I think yeah.
He says, I'll say that the tau max 1.5 tau average is good for yield, but conservative for ultimate.
Okay.
Yeah, so yes, you can use 1.5 or you can check the textbook specific for solid circular cross section. The maximum shear stress is to be 4 shear force over 3 cross section area.
Oh, okay.
Yeah, it's not a VOA, just don't use a VOA. And 31, page 31. I don't think you should do fatigue analysis in this way. I think I use example for use aircraft example in the class, like fatigue analysis for aircraft, like during flight, back, because aircraft you really need to, that is for fuselage, yes, like during flight, there's tensile stress, foot stress, on shear stress and on the ground back to zero. So it's like it's very simple, like zero maximum, zero maximum, zero maximum. That is for aircraft, but for fatigue analysis of our spacecraft, I mean, how many flight cycle you will have? I don't think it's really necessary to do fatigue analysis like this. What I mean for the fatigue analysis for the spacecraft, you probably more consider the vibration generated by engine or anything. Some group even use like the regularly split the structure and what is the fatigue that causes the structure to. Also, if you're really like flight cycle, I don't think it's really necessary. I mean,
Makes sense.
yeah.
He also added, really in industry, the fasteners will have an allowable shear force and you'd use that back for the.
Yeah.
Yes,
Sure.
yes, that'd be good. This is 31, right? 32. Oh, okay. So I feel like for the thermal analysis, it's more like this is a slide for the thermal analysis. I want to know, I use this one as example, so I want to know a structure of the whole thermal analysis itself. So thermal analysis, like we want maintain some temperature or want to get out some heat. So the first thing we need to figure out what the requirements. So how much heat we need to get rid of, like how much power system, like an electrical system, will generate heat, and all this heat you need to find someone to get rid of, right? So that is like the big goal. Or like I want to maintain inside temperatures in certain level, or the outside temperature is certain level. So I have a clear goal at the very beginning. This is the thing that we need to do, 3-hour thermal analysis. And then what is our solution? And then what is our analysis? And then in the end, is our solution, is our design satisfy the requirement? That is a big structure with thermal analysis. What you give here right now, I don't see the structure here. That's what I mean. It's more like the some detailed information. Probably it's not enough. Yeah, that's what I mean. I want to some real analysis of this part and show the logic connection of each detail. And also, one other thing is the Q&A part. It's amazing job. But I wish I could see more involvement from other students. Because we do have it's a group project. It's like, just imagine if several years later that you guys come back and you want to hire someone, and who you want to hire if only if you don't really stand out and show yourself, right? So but of course they did a great job. That's absolutely, but I wish I could see more involvement from the students. Yeah, so if you can just see this, and it's not criticize anybody, just see this a opportunity to show yourself, right? Yeah. So,
Thank you.
thank you, congratulations. Great job.
Yeah. I saw you good.
We got 10 more minutes, so it's enough time. So I guess since she had her bout with the material science of this, my bout is on the effects, because we had already talked a little bit about the electromagnetics